welcome back to the session, right. So, in this session we will discuss about the response of second order system. So, we will apply here some standard test input. Depending on that, we would like to see what would be the response or output of the system. Okay. So, last time we were discussing about the second order system. We had seen the indicating device and series RLC network, they will belongs to the category of second order system. Okay. And we had check out their standard equation, and we were also calculating the roots of equation, or you can say poles of equation. So, if we continue our analysis, then we will see basically the response of second order system in terms of omega and omega d and zeta. Okay. So, in today's session we will discuss about the impulse response, time response, you can say step response, and time response specification, right. So, here in the second order system we are getting the different response on the value of zeta here. So, if you remember the previous root, that is S equal to minus zeta omega n plus minus under 1 minus zeta square. Okay. So, we had obtained this expression where minus zeta omega n was the actual damping, okay, and we had given a new term, this was j was here, it is omega d. Okay, actually omega n would be here, it would be j omega n, right. So, this term would be omega d, this is the damped frequency or damped system, or you can say damped response, right, where omega d is equal to omega n under root 1 minus zeta square. So, this thing we had discussed in the last session. So, if I vary the value of zeta, then S value, or you can say pole value will change. So, whenever my first case you can say when zeta is equal to 0, then what will happen? So, S would be equal to, you can say this term will be 0, and second term would be what, j omega n under root 1 minus zeta square is 0. So, I will get here basically the plus minus of imaginary term or imaginary root. Okay. So, if I plot it on the imaginary plane, so I will obtain my roots on this equation, on this you can say imaginary axis. So, if I see response in the time domain, we will get here a sinusoidal oscillation. Okay. So, whenever my zeta is equal to 0, so we are saying this category is undamped. Okay. In the same way, whenever I put zeta value greater than 0, but less than 1, so this will come under category of under damped system. Okay. What would be response, we will see later. Okay. In the same way, when I put here zeta equal to 1, in that case my you can see here S equal to, when zeta is 1, is equal to omega n plus minus j omega n is here, and if you can say zeta is equal to 1, this whole term will become 0. So, you will get here only S equal to omega n, right. So, in this case what will happen, you will get here a critically damped system, there would not be any oscillation, you will get here a real value, right. So, such type of system is critically damped system, and whenever my zeta is greater than 1, then I will get here a over damped system. So, how it will come, we will see in the next slide. Okay. So, we will see here damping and types of damping. So, the damping basically depends on zeta, you can say they are the opposing force which will suppress the oscillation in the system. Okay. So, if I vary the zeta, then I will get the 4 type of system. One is the over damped, whenever my zeta is greater than 1, and we are saying our system is critically damped. So, in this case our system will go like this. Whenever I provide a step input, my response would be like this for critically damped system, it means it will not contain any oscillation. Second case is critically damped, whenever my zeta is equal to 1, right. So, in that case I will get a response like this, it is a very fast response, and immediately my response will reach to the value of 1. So, it is a very fast response as compared to over damped, and it also comes in category of ideal system. So, whenever I have to make a very fast system, so I have to approach this critically damped system. again in the response you will not get any oscillation. Third case is here under damped system, whenever my zeta is greater than 0, but it is less than 1, in that case I will get a certain oscillations inside the system, right, and this frequency would be omega n, and later as time increases it will suppress to 0 because of finite value of zeta. Okay. In that case I will get a damped frequency that would be omega d. Okay. And we discuss what is omega d, and in undamped system what will happen, my zeta is equal to 0 and you will get a sustained oscillation as the output. It means whenever my zeta is equal to 0, I will get a sustained oscillation at the output. Okay. So, we will see the response of this. So, here whenever my system is, you can say, over damped, slowly my system reaches to the desired state. So, here I am applying the step input, this is the response of step input. So, I applied the step input and this is the output curve is coming. So, this red line is basically my input and remaining blue line is the output. So, here you can see in the case of over damp, when zeta is greater than 1, system is slow and sluggish and slowly it reaches to the level 1. Whenever I am going for critically damp, my system immediately or faster than over damp, you can say faster than this case, reaches to the level 1. Okay. Whenever I am going for zeta, you can say less than 1, but greater than 0. So, I will get here under damped system, I will get a oscillation like this and will sustain to the, or it will stop to the level 1. Whenever my zeta is equal to 0, this is my undamped response. Okay. So, this is a time domain behavior. Whenever I apply a step input and if I vary the zeta value, this 4 type of response is coming at the output. Okay. So, if I plot this, because when I consider that zeta is equal to 0, so I am getting here this type of imaginary pole. So, this is the undamped system. Whenever I am getting zeta here, real and imaginary part both is having, you can see when zeta is greater than 0, but less than 1, this will belong to a category of under damped system. Okay. Whenever my zeta, or you can say roots, you can say, because zeta is function of what, roots of this equation. Okay. It means if I change the value of roots or pole, then zeta will vary. Okay. So, whenever my roots are real, but they are different, so it will come under category of over damp. You can say one value is here 3, second value is here, suppose it is 4 or 5. Okay. So, this will be the case of over damp where zeta is greater than 1. So, this is the basically location of poles and roots whenever I am varying the value of zeta. Whenever I am getting the real roots, but they are repeating on the negative real axis. So, this will gives me the case of critically damp where my zeta is equal to 1. So, for all the case wherever my zeta is equal to 0, less than 1, but greater than 0, equal to 1 and greater than 1, I am getting this location of poles. Okay. So, this is the plot on the imaginary axis. So, this is the case, you can say undamped, under damp, this is the critically damp, roots are repeating, real roots, and distinct root or distinct real root will be over damp. Okay. So, now we would like to see the impulse response of second order system. So, here this is the transfer function that we had done this calculation. Here I am assuming R is equal to 1. So, okay, for different value of zeta I would like to see what would be the impulse response. So, first I am assuming here zeta equal to 0, this is the undamped system. Okay. So, y is given like this, okay, and I would like to know what would be my y t. So, I have to take Laplace inverse of it, because I need to obtain my output response in terms of time domain. So, this is basically gives you a sine term, you can say omega n sine omega n t if you take Laplace inverse of it. So, I will get a sustained oscillation at the output whenever my zeta is equal to 0. So, this is the impulse response of second order system for the case zeta is equal to 0. When I consider the underdamped response or underdamped system for this value of zeta, I will get this equation, and then after simplification I will get omega n square over this equation. Okay. So, how it is coming? So, what I am doing here basically I am making this square. So, this equation is s square plus 2 zeta omega n s. If I have to make it perfect square, so what I will do? I will add here zeta square omega n square and subtract by zeta square omega n square, and plus omega n square will remain here. Okay. So, this term will become what? S plus zeta omega n whole square, and this term if I take common omega n, this will become 1 minus zeta square. So, here it is what j term is coming, it can be obtained if I make the form of a square minus b square. It means I have to obtain here minus sign. So, how it is possible? So, here I have to make this term minus of j, if I add here j square here. So, the you can say this minus of minus you can say j square omega n square 1 minus zeta square. So, if you open it you will get this term in the denominator. Okay. Now, I have to do what? Just separate it, you will get this term basically in the denominator. Now, I have to make it in time domain. So, I have to take the Laplace inverse of this whole equation. So, till now I am getting this equation, that is omega n square over you can say s plus zeta omega n square plus omega d square is here. Okay. So, if I have to make the perfect inverse, if you have to obtain time domain, so this will become what? I have to add here you can say a term which is omega d in numerator, then this whole term will become a sin omega dt, right, if you remember this term sin omega dt from the property of Laplace inverse. So, I have to add omega d in numerator. So, what I will do? I will multiply by omega d and divide by omega d. Basically, omega d is what? Omega n under root 1 minus zeta square. So, I can write this equation as omega n multiplied by omega d divided by under root 1 minus zeta square, because this omega n and numerator square power will cancel out. So, this expression is written here, you can see, and if I take the Laplace inverse of that, this will come at the output. This is the sine wave omega d over s square plus zeta omega n plus omega d square. Okay. And s plus zeta omega n term coming in numerator. So, this will be the exponential term present in the response. Okay. Now, we will see the impulse response when zeta equal to 1. In that case, we need to put here zeta equal to 1, this would be the expression, this will become like this, and I have to take it Laplace inverse, I will get a response like this. Okay. So, if I see the output response in previous case, so this is my output response. I applied the impulse signal in the input and here I am getting this output. Okay. You can see a very small type of oscillation present because it is under damped system and it dies out as time increases. For critically damped system, you applied the impulse, it will try to increase just like it will try to behave just like the impulse, and then it will dies out to 0 without any oscillation, because it is belong to the critically damped system. So, this is the output response when zeta is equal to 1. When we consider the case of over damped, my output response would be like this and slowly it will goes to value 0. So, if I solve it this equation just like this. Okay. So, this is basically the omega d, this thing we have done in the previous slide, this is basically omega d, j omega d you can say. Okay. J term will come. So, here y t is coming like this after taking Laplace inverse, and this would be the graph. Okay. Now, we would like to see what would be the step response for different value of zeta. So, here I am applying the step input 1 over s, you can say here my input would be this step signal, this is time t equal to 0, value is 1 continuously. You can see this red line is my input and this blue line is the output. So, when I put zeta equal to 0 for step response, I will get this expression, because y s will be transfer function multiplied by r of s. R of s is 1 by s. So, 1 by s coming in the multiplication. So, for zeta equal to 0 undamped system, this is the expression. Okay. So, from partial fraction I can separate out this term. Now, I need to take y of t, so that I will obtain this time domain expression. So, if I take Laplace inverse, so I will get 1 minus cos of omega n t, and this will be the graph for it. Now, we are very interested what will happen when I apply here zeta less than 1 and but its value is greater than 0. Okay. So, this will be the underdamped system, this will be the expression, my input would be 1 over s. Okay. After you can say partial fraction, I will obtain it. Now, further I can simplify it, this 2 zeta omega n can be written as zeta omega n plus zeta omega n. Okay. And this term we had seen in the previous slide how to obtain it. Okay. So, I can separate out s plus zeta omega n in numerator with this denominator, plus I will separate out zeta omega n, you can say zeta omega n divided by this term in the denominator. So, here I need to take a Laplace inverse of whole, so that I can obtain my response in time domain. So, what I am doing here basically, it is 1 over s, Laplace inverse is 1. So, here it is s plus, you can say it is s over s square plus omega d square. So, if you take the Laplace inverse, you will get cos of omega dt, but here with the s term, s plus zeta omega n is coming. So, you will get an exponential term of minus zeta omega n t, right. In the same way, we would like to write the, you can say, Laplace inverse of this term. Okay. So, it is basically what zeta omega n over s plus zeta omega n whole square plus omega d square is here, right. Now, what I will do, I have to solve it, I have to take Laplace inverse, it means in the numerator omega d should come. So, omega d is missing. So, I am doing what, multiply with omega d divide by omega d in numerator, so that it will become sine term in time domain. Okay. So, omega d you know very well, it is omega n under root 1 minus zeta square. Okay. So, just do this. So, that is why this will become what, zeta omega n by omega d, that is omega n under root 1 minus zeta square, and I am doing the same multiplication of this, right. This term will cancel out. Okay. And you will get omega d in numerator, you can say you will get here zeta omega d in numerator divide by, you can say, under root 1 minus zeta square will remain, omega n यहाँ पे cancel हो गया, and in the denominator term you will get s plus zeta omega s square plus omega d square same. Okay. So, if you take a Laplace inverse, this will become sin omega dt. With s term you can check s plus zeta omega n is here, it will gives you the exponential term of this, right. I hope this thing is clear to you. So, if I further solve it, so this will become expression like this, exponential minus zeta omega n I am taking common, and this term I am taking common. So, this will come outside and this will be in multiplication with this term. Okay. So, if you remember, we had calculated the value of poles for second order system. If you remember that zeta omega n was the real value, and this was the, you can see, omega d, that is the omega n under root 1 minus zeta square. If we calculate the cos theta, then what would be value? It would be zeta. We had done this calculation. So, here what will happen? This zeta will replace by cos theta, right. In the same way, this 1 minus zeta square, this term will be replaced by sin theta. If I calculate sin theta here, so this will be here a sin theta term. Okay. So, this will become sin theta cos omega dt, cos theta plus multiplied by sin omega dt. This will make a sine cosine function. If I solve it, this will become sin omega dt plus theta. Okay. So, where theta is basically you can say cos inverse of this and sin inverse of this, whatever it will have this value in cos term, this value in sin term. So, this is my output response whenever I am assuming zeta is less than 1, but greater than 0. Okay. So, we will consider this output response in upcoming session for further derivation. Okay. This is the detailed steps, you can see whatever I discussed, it is given in this step. So, you can refer this slide, you can read it out, it is same, giving the same output, right. Now, I would like to see what is my output response for this case when my zeta is less than 1, but greater than 0, under damp, this type of response is coming, and this is my input, and this oscillation present at the output, and the frequency of oscillation would be omega n, but it keep going on decreasing, then frequency would be omega d. Okay. So, here I am keep varying the value of time t, 2t, 3t, 4t, where value of t would be given by pi over under 1 minus zeta square. So, this is the response whenever I change the value of zeta. So, when zeta is 1, this is the response. When zeta is greater than 1, I am getting the sluggish response. Okay. When zeta is very small 0.1, I am getting the maximum oscillation inside the system. Okay. So, if I keep make high value of zeta, oscillation will be minimum. If I keep value of zeta minimum, oscillation will be maximum. So, here we can say zeta is damping factor or a factor which will oppose oscillation. Okay. So, if you keep minimum zeta, oscillation would be maximum. If you keep zeta value high, it will suppress the oscillation. Okay. Then step response for critically damped system, it means zeta equal to 1. So, here in this equation I will put zeta equal to 1, this will become okay 1 by s, again step input is here. So, if I have to obtain y t, take Laplace inverse of it, this will come after a partial fraction, and after inverse this is the expression, and if you plot you will get response like this. This is happening in critically damp. Okay. So, in the same way we will see the various step response okay, in S plane. So, here if your poles are real okay, and lying in the left half plane, you are getting response like this. Okay. So, this type of graph we will obtain whenever you are getting repeating of poles on the real axis, you are getting a critically damp fast response, this is slow response, this is the case of over damp when zeta is greater than 1, this is fast response when zeta is equal to 1, here this is the under damp response. Okay. So, this is happening when my poles lying in left half plane, and same way when my poles on imaginary axis I will get oscillation, this is the undamped. Whenever my poles in right half, we will get response like this, my response will keep increasing with respect to time. If my real poles they lie in the right half plane, I will get a response like this. Okay. So, in unit 4 whenever we discuss the stability, then we will discuss about it. So, this is the response whenever my input is step signal. Okay. So, now we will see the basic time response specification. So, this is the time domain specification when my input is step response and I am considering zeta value less than 1, but greater than 0, that is for under damped system. Okay. So, for under damped system, these are the various definition. One is delay time, right, whenever my time response reaches to the 50% of the final value, that time interval would be T d. Okay. So, I will show you in the following graph, right. So, this time interval is T d, delay time, this is my input, desired output basically, this red line. Okay. So, whenever I cover the 50% of this, you can say my output is going like this. So, 0.5 50% is here. So, this time interval basically gives me the delay time. Okay. In the same way, if we check the rise time, So, it will tells the time interval between 10% to the 90% of the output and final value. So, here basically if I would like to see the rise time, I will take 10% 0.1 this point, then 90% is this point, the time interval between them would be rise time T r. Okay. In the same way, if we see the peak time, this is the time or instant of time at which I will obtain the maximum value in the output. So, if you see I am getting the maximum value at this time instant. So, this T max is basically the peak time T p. Okay. So, this is the peak time, and if we see the peak overshoot M p. So, this is what is different between the peak value of time response and the steady state value. Okay. So, here if you see the peak response is coming, let me show the graph. This is the peak response is coming, and in the steady state I am reaching to the value of 1. The difference between these two value would be the maximum overshoot. So, this value I am saying in this expression is y t p. When time response tends to infinity, it is basically equal to 1. So, y t p minus 1 divided by y infinity 1 into 100%, this will gives me the peak overshoot. So, right. So, in the next lecture we will discuss the mathematical expression of these term. Okay. So, thank you for today. We will continue in next lecture.